Assalamu alaikum. So today we will solve assignment number 1 of our course Methods and Principles of Nuclear Tracks. So this is our assignment number 1. Today I will let you know how you can solve this complete assignment step by step. Okay. So these are total 8 questions we will do in this video. So stay tuned with us and watch. So what's the first question basically? The question is estimate the time required for a 5 mega electron volt alpha particle to slow down and stop in silicon. Okay, it means you have to find the time required. Okay, basically you already know stopping time you have to find, but we already discussed in our previous videos. Okay, of a alpha particle, 5 mega electron volt alpha particle, which is going and it slow downs into the silicon, and you have to find the time required, means stopping time, and repeat the same case for same particle, means same alpha particle now is slowing down in the hydrogen gas. So in this problem you have to find two things. Okay, stopping time in when your alpha particle slow downs in silicon and when your alpha particle slow downs in hydrogen gas, while your energy is 5 mega electron volts. So let's start. So you can see this is basically the solution for this problem. How you can find, basically you can see the energy is okay, we already know the mass of an alpha particle, which is 4 amu, and energy which is given is 5 mega electron volts. You have to find the stopping time. Okay, for the first case you have to find the stopping time for the silicon. Okay, we already know the formula for the stopping power is, which is T equals to 1.2 multiplied by 10 raised to power minus 7 r under the root. Ma means mass of the particle, okay, coming particle, and divided by energy. So this is the complete formula how you can find the stopping time. Here m we know, mass number of the coming particle, don't worry about this, and energy is also mentioned, which is 5 mega electron volts. The only unknown thing which we have to first find is the r is basically the range of that particle. So first of all we will find range, then we have to put that range in this, and then we will calculate the stopping time. So to calculate the range, if your range is below than what I can say, below than between 4 and 15 mega electron volts, you have to use this formula. Okay, range, if you want to calculate in millimeter, 0.05 T, which is the energy, plus 2.85 bracket close T power 3 by 2. Okay, but there is another formula. You can find the ratio of r1 divided by r2 equals to rho 2 by rho 1 under root a1, which is the basically the mass number of, and divided by a2. Okay, so this is in our scenario, r silicon, range of silicon divided by range of alpha particle equals to rho alpha, rho silicon, mass number of silicon and alpha particle. These all aspects are only just given to you while solving this problem. The only thing you have to find is the r silicon, range of silicon. After calculating you will get the range of silicon, which is 22 multiplied 10 raised to minus 6. Okay, after putting this range in this formula, 1.2 into 10 raised to minus 7 is already here. 4 is the, is the mass number of the alpha particle, and divided by 5, which is the energy. After substituting you will get your stopping time in case of silicon. But what in the case of hydrogen gas, same you have to do procedure for hydrogen gas, and you will get your range, which is then equals to 0.1. okay, after putting this range, and you will get your range in, you will get your stopping time in when your alpha particle is going into the hydrogen atom. Okay, so this is how you can solve first problem. Okay, now you can see what's our second problem. How many 5 mega electron volt alpha particle are required to deposit a total energy of 1 joule. Okay, how many 5 mega electron volts alpha particles? Okay, you have to calculate how many particles should be there if you want to deposit the total energy of 1 joule. Okay, so you have to find the number of particles, how many particles you will generate when the total energy was deposited to be 1 joule. Okay, so here how you can find, it's a very simple problem. What you have to just do, You already know 1 mega electron volt is basically equals to mega, which is 10 raised to power minus 10 raised to power plus 6, and electron volts, which is 1.6 into 10 raised to power minus 19. So 1 mega electron volts basically equals to 1.6 into 10 raised to power minus 13 joules. Okay, now but in our problem the given condition is 5 mega electron volts. Okay, so the 5 mega electron volts alpha particle required to deposit 1 joule, only you have to take the ratio, which is the, because you know we have to find the number of particles. Okay, in this case, so we have to take the ratio. So 1 joule over 5 mega electron volts, because we have to deposit 1 joule of energy, and the energy which is the required case is 5 mega electron volts. So 5 mega electron volts equals to 5, which mega electron volts basically equals to 1.6 into 10 to the minus 13 joules. After dividing 1 divided by taking the ratio, you will get the number of particles. So this is the number of particles, 1.25 into 10 to the 12. Okay, so these are the alpha particles. If they get this 5 mega electron volts energy, they will deposit 1 joule of energy. Okay, so what's our third problem? Our third problem is calculate the stopping power. Okay, now you have to calculate the stopping power due to the ionization and excitation of 5 mega electron volts electron, okay, moving in water. Now energy is 2 mega electron volts, and now the important thing is you have to find the stopping power, and now electron is moving inside the water. Okay, this is a different scenario from the first problem. What is the radiation energy loss of the particle, what is the total energy radiated. Okay, so let's start. You will find the stopping power when your electron is getting into the water with an energy of 2 mega electron volts. So this is how you can solve this problem. Okay, so we already know specific energy loss due to the ionization and excitation is given by this formula. This is a very large formula, don't worry, this formula must be given in your papers. Okay, so this is our basic formula for the specific energy loss when an electron is going inside the medium. Okay, so dE by dx means stopping power in mega electron volts per meter. This is basically equals to 4 pi r naught square m naught c square divided by beta square n z ln of beta gamma under root gamma minus 1 divided by I, okay, mc square plus 1 by 2 gamma square multiplies by gamma minus 1 whole square divided by 8 plus 1 minus bracket gamma square plus 2 gamma minus 1 bracket close ln of 2. This is a very large formula. You don't have to remember this formula, this must be given in your papers. Okay, there are many constants. Okay, so this constant is equals to 4 pi r naught square, which is equal to 10 raised to minus 28 meter square. And another constant m naught c square is also equals to 0.511 mega electron volts. And the energy in our problem, which is already given, is 2 mega electron volts. What is this I? Basically, you already know that this is the ionizing potential. Okay, and this is the formula of this I is basically in electron volts is equals to 9.76 plus 58.5 z power minus 1.19 bracket close z. Okay, this is the formula. This basically works purely perfectly good when your z is smaller than 12. Okay, and the other factor that was unknown is beta and gamma. So to find beta, there is a formula to find first of all gamma. The formula for gamma is T, which is the energy, plus m naught c square divided by m naught c square. T in our scenario is 2, and m naught c square you already know, constant 0.511. Okay, so this is after calculating you will get your gamma, that is equals to 4.913. And similarly there is another formula to find beta, that is equals to under the root 1 minus 1 divided by gamma square. So after putting the value of gamma, you will get your value of beta. Okay, so you will get also beta square. And there is another value, that is a capital N. Capital N is basically the product of density multiplies by Avogadro number divided by the A, okay, which you already know is the mass number. Okay, and small z for the case of electron, and for the case of electron and positron, your small z always equals to 1. Okay, you have to remember this. And capital Z you already know for case of this depends upon material to material. Let's substitute all values in our formula and we will calculate our problem. So you can see this is the value 4 pi r square, which is 10 multiplied 10 so minus 28, m naught c square, which is 0.511 divided by, okay, beta square. And similarly this is we see that n and this is the capital Z. And after putting the values of density, and we will put the density of what water, okay. And our, in this case, A is basically the mass number. After calculating, you will get this, okay. And this is the Avogadro number divided by A, okay. 2 multiplied 10 is from -3, okay. And Z for the case of electron, as I told you, is equals to 1, okay. And all other aspects ln this, okay. You just have to put the values. Let me show you, okay. You can see here, this is ln, okay. You put the value of ln, and now again beta, gamma, and this is the value of after calculating gamma -1 and taking under root, you will get 1.978, okay. And then m naught c square value, okay, divided by I, as I told you. And for the for the case of water is basically equals to, okay, it is 20.4, okay, 10 raised to power minus, okay, -6. Similarly, 1 by 2 gamma square, 1 by 2 gamma square, and all other values you will put after calculating. You will get your final expression, which is equals to 188 mega electron volts, okay, per kg per meter square. And you have to, you also converted this into you can convert this into, okay, like joules, okay, joules. But this is for the case of hydrogen. As I told you, electron is moving into the water. So water, you know the formula of water, chemical formula is H2O, 2 molecules of hydrogen and 1 molecules of oxygen, okay. First I calculate all the things for hydrogen, that's why I use the capital Z equals to 1. But when I solve for oxygen, I will use the mass number of oxygen. You can see here, let me show you this 8, okay. First of all, I will calculate for hydrogen, then I will calculate for oxygen, then finally I will combine both to get the final stopping power expression for when your electron is stopping into the water, okay. So hydrogen is done. Now you have to calculate same procedure for the case of oxygen. The only thing is this changes, which is the atomic number changes and density changes. You can see here density changes. Here the density for hydrogen H2 is 20, here the density is 16. You have to multiply it by, okay, you in here, okay, density of hydrogen atom is 1, but for H2, so it becomes 2.015, and the density for only O is 16, okay. You have to multiply 10 to -3 here, 10 to -3 here also. And I value for the case of hydrogen atom is 20.4, and I in the case of oxygen atom is let me show you this 115.7, okay. This you will calculate by this formula after putting the value of Z, okay. So this is whole procedure. You will find your expression, okay. For oxygen, you will get your final expression in joule per joule per kg, joule per kg per meter square. This is equals to 3.01 to multiply 10 is power -14. The next thing is you have to just add up, because for that you must have to know the probability, the percentage of how many percentage of water means the water, the mass percent of hydrogen in the H2O, and the oxygen percent mass in the H2O. Basically the hydrogen percentage in water is 11.11%, and in water oxygen percentage is 88.89. So we have to multiply our answer with their percentage. 88.89 becomes 0.88 and 11.11 becomes 0.11. Just multiply with corresponding values and just add up. You will get your final expression. So your stopping power in water while when your electron is going inside your water is 20.84 mega electron volts kg per meter square, okay. So this is our problem number 3. So let's do our third problem. What's basically our fourth problem. Now we have to see our fourth problem is basically calculate the stopping power in aluminium for 6 mega electron volt alpha particle. Now the same thing, you have to calculate the stopping power, but now in aluminium, and the energy is 6 mega electron volt and your particle is alpha particle. So this is how you can calculate the stopping. power in aluminium, okay, for a 6 mega electron volts alpha particle. As we already know, the mass number of aluminium is 27 and density of the aluminium is 2.7 grams per centimeter cube, okay, and the atomic number of aluminium is 13, and your density in kg is 2710 kg per meter cube, okay. And as we already know, to where the formula to find gamma expression is T plus m naught c square divided by m naught c square. T is basically the energy, and m naught c square is direct value we already know is 0.511. If not, you can also use by this 0.511. You can also substitute, you will calculate gamma. And to calculate your beta value, there is a formula, as you already know. Beta is equals to under root 1 minus 1 divided by gamma square, okay. And this is basically value of beta square. Take under root of this, you will get your beta. Take square of this, under root of this, you will get your beta value. And because this is not an electron, this is basically the alpha particle. So there is another expression to find the stopping power. This is a quite short, a little bit short from previous formula when an electron is going, but this is for if proton or alpha particle is inserting in some material. So the formula is 4 pi r naught square z square m naught c square divided by beta square n capital Z bracket ln of 2 m naught c square beta square gamma square divided by I bracket close minus beta square. So this is how you can find if your alpha particle, okay. These constants are again same. 4 pi r naught square equals to 10 raised to minus 28. Z basically now small z is now equals to 2, because for the case of alpha particle, as in previous, it's basically equals to 1 because that is electron. M naught c square, which is 0.511 mega electron volts, okay. And this is capital Z. We know the capital Z for the case of aluminium is basically equals to 13. And to find this I, and we already know the formula, 9.76 plus 58.8 z power minus 1.19 bracket close z. So this is how you can find the value of I. After substituting the value of Z, which we know it is 13 for the case of aluminium, we will get our final expression for the case of I is 160 electron volts. Now you have to substitute all your values in your stopping power formula. This is 10 raised to minus 28 4 pi r square and z square, which is we know 2 square, and m naught c square 2.511 divided by beta square values this, and small this n, okay, which is the density, n basically equals to density and Na divided by A, you can see here, and this is A basically equals to 27, but you have to multiply it by 10 to minus 3 here. Again capital Z is equals to 13 ln 2m naught c square means 2m naught c square value, beta square value, gamma square value, okay, divided by I, which we know 160, but you have to multiply it by 10 to minus 6. Again you can see minus beta square. Substitute all and you will get your final expression in mega electron volts, which is equals to 150,789.3 mega electron volts per meter square, okay. And this is in joule per meter square after putting the value of mega, which is 10 raised to minus 6, and electron volts value, which is 1.6 into 10 raised to minus 19. Multiply both these and multiply with your final expression, you will get your final answer in joule per meter, which is 2.4 into 10 raised to power minus 8. This is basically the stopping power of aluminium for 6 mega electron volt alpha particle. Now we have to go for further for our fifth problem. And our fifth problem, you can see here, we have to find what is the range of 4 mega electron volts deuteron in gold. Now we have to find the range, and our energy given is 4 mega electron volts, and our particle is deuterium, and this is going inside the gold. So here you can find the range basically, okay, and there is a formula for the alpha particle, which is the ratio of m alpha divided by m for deuteron basically equals to energy for deuteron. Basically this is the ratio of energies ratio divided equals to masses ratio, because we find the energy. First of all, we need the energy, okay, for because you can see, okay, because we need the energy, and energy for the alpha particle is 8 mega electron volts, okay. Now we have to find range, and we know if your energy is greater than, okay, and 4 and between 15, we have to use this formula, that is 0.5 t plus 2.85 bracket close t power 3 by 2, okay. this is our expression. Now you have to put the value of t, which we already find, which is equals to 8 and 8, and after substituting you will get your answer. Range of alpha particle is 735 millimeter. Okay, now the range of 4 mega electron was deuteron in air we have to find. Okay, and for this we will find, this is our formula of range of deuteron. This is the range of alpha particle, but we have to find range of 4 mega electron volts in deuteron. For the case of deuteron there is another formula which is equals to 2 of range of alpha particle minus 2 range of alpha particle, which we find 735 and minus 2. Okay, and this is our final expression, 145 millimeter, which is equals to 0.145 meters. This is our range in deuteron. But now for the case of gold, we know the formula, basically Rd divided by R of deuteron, because I multiply R deuteron, R alpha by R, okay, to other side, which is this 3.36 multiplied by minus 1 equals to this. This is the formula as I already show you here. Okay, this formula I'm using here, let me show you again. This formula, okay, R1 by R2 equals to rho 2 by rho 1 under the root A1 by A2. This formula I have to use here, and I will get my final results for my R deuteron, stopping the range of R deuteron in gold. Okay, so this is 0.035 millimeter, which is equals to 35 mu meter. Now our sixth problem, what we have to find is, we have to calculate the stopping power of copper. The atomic number is 29 and our mass number is 63.5 for a proton having z equals to 1, traveling at 50% of the speed of light, where the beta value is 0.5. Assume the mean excitation potential of I. Okay, for the copper is 322. Okay, so mean excitation potential, the value of I is given, which is 322 electron volts, and atomic number and mass number of copper is given, and the value of beta is also given, that is 0.5. But we have to find the stopping power of copper. Okay, use a specified version of Bethe formula and approximate value, and you have to calculate the stopping power by these aspects. Okay, so let's calculate. Okay, now this is our formula, because in this again there is not an electron, there is a proton. For the case of proton, for the case of alpha particle, the formula is same, which we use in our problem number 4. Okay, the formula is same. I wrote here. Again we can calculate but now here we don't use the value of beta formula, because beta is now again already given, that is 0.5, and beta square equals to this. And for but here gamma is not given, but we can calculate gamma from beta, because we know the expression of gamma in beta, that is gamma is equals to 1 divided by under the root 1 minus beta square, putting the value of beta square, and you will get your final expression, and that is equals to 1.154. okay, and I again the excitation potential is now given, you don't need to find. Okay, there is a formula of I, but here is already given, and small z is also given. For the case of proton, it always 1. Okay, but here our material is copper, and z is also given, that is 29 here, and the capital N, there is the expression, so we already know how we can find capital N. Basically the density, Avogadro's number multiplies by the mass number. Okay, so after substituting you will get the density of, okay, copper is 8850, okay, kg per meter cube. Okay, so this is how you can find density. Putting the value of density, you can find your final expression for N, that is equals to this, and m naught c square you already know is equals to 0.511 mega electron volts, and 4 pi r naught square is, you already know, 10 raised to minus 28 meter square. Now you have to put all these variables inside your formula to calculate your final expression. Okay, to calculate the stopping power of copper while it is traveling at 50% of the speed of light. Okay, so I am putting all these values in. Okay, 4 pi r naught square, z square value, m naught c square, beta square. Okay, these all other values, basically, okay, this is z, this is the value of n, capital N, and all other values multiply, and you will get your final expression in mega electron volts is 338. Okay, mega electron volts per meter, and in the case of joule per meter, you just have to multiply your answer by 1.6 into 10 raised to power minus 13, and you will get your final expression for your stopping power of copper, okay, for proton, okay, while it is going inside copper, is basically equals to 5.34 multiplied 10 raised to power minus 10 joule per meter. So what's our second last problem? Our second last problem is basically problem number 7. What we have to find? We have to find, okay, gamma rays of intensity I naught is equals to 10 Weber per meter square passes through 10 centimeter thickness sheet of aluminium. The density of aluminium is rho 2.7 gram per centimeter cube, and the mass attenuation coefficient is 1.0.1 centimeter square per gram. You have to calculate the intensity of the gamma rays after passing through the aluminium, okay. So the intensity of gamma rays already given, that is equals to I naught is equals to 100 Weber per meter square, and the thickness of the aluminium sheet is also given, that is 10 centimeter, and the density of the aluminium is also given, which is in grams per centimeter cube, and that is 2.7, and the mass attenuation, that is very important, is also given in your problem, that is equals to 0.1 centimeter square per gram. But you have to calculate the intensity of gamma rays after passing through the aluminium. So this is very short and important problem. So this is your solution, how you can solve this problem. Basically, as we already know, there is an expression I equals to I naught e power epsilon exponential power minus mu x, okay, where you know I intensity, and where the mass attenuation is equals to mu by rho, okay. But here mass attenuation is not given, okay. Mass attenuation is given and density is given. So with the help of mass attenuation and density, we can find mu. So mu becomes equals to mu m multiplied by mu rho. So mu m multiplied by rho, mu m is given, which is 0.1, and rho is given, which is 2.7, you can see here, and you will get your mu, which is equals to 0.27 per centimeter, okay. So now you just have to multiply mu with x. So you can multiply mu with x is given, which is 10, and you will get your mu x now equals to 2.7. Now you have to take put all these values in this formula. I equals to I naught is given, which is 100, okay. E power minus is as it is, and mu x value is 2.7, which we find okay here. So the unit of intensity is always Weber per meter square. So after calculating, you will get your final expression for the intensity of gamma rays when your I naught is 10 Weber per meter square, is basically equals to 6.7 Weber per meter square, the intensity of gamma rays after passing through the aluminium. So this is how you can find. So our last problem of our assignment number 1 is basically a material contains 5 multiplied 10 raised to power 22 nuclei per centimeter square, okay. There is a material which contains how many number of nuclei? 5 multiplied 10 raised to power 22 nuclei per centimeter cube, okay. The microscopic absorption cross section of the neutron is 2 barns, okay. The microscopic absorption cross section is given, which is equals to 2 barns. You have to calculate the macroscopic absorption cross section, okay. You already know that the microscopic absorption coefficient is basically the sigma, and so basically let me show you, okay. So you have to find the macroscopic absorption cross section. So here how you can find, as we already know as expression to find the macroscopic absorption coefficient is basically equals to summation, okay, equals to n sigma, okay, whereas n is basically the number density of the nuclei and sigma is basically the microscopic absorption. You just have to multiply your microscopic absorption with your number density, you will get your macroscopic absorption coefficient, okay. So this is very quite simple problem. So here is the value of n, which is given, which is the number density of the nuclei, and there are 5 multiplied 10 raised to 22 nuclei per centimeter cube, and the microscopic absorption coefficient is given, which is 2 barns, and 1 barn is equals to 10 raised to minus 24 centimeter square. We already know about this, okay. So after multiplying this, you will get 2 multiplied 10 raised to minus 24 centimeter square. Now you have to this is 2 barns equals to, okay. So now you have to multiply n with your sigma a. So this is the value of n, number density of nuclei, and this is the value of sigma A, 2 bonds. After multiplying, you will get your macroscopic absorption coefficient is basically equals to 0.1 per centimeter. Okay, so this is the macroscopic absorption cross section of the material. How you can find with the help of microscopic, how you can find the macroscopic absorption coefficient of the material. So that's all for today. This is our assignment number 1 of advanced methods and principles of nuclear tracks, which we solved today. Okay, so these are total 8 problems. We all did this. So that's all for today. So thanks for watching and stay tuned with us. We will upload all videos for this course, and Allah Hafiz.